A very good morning to everyone. We welcome all of the honorable dignitaries, learned delegates, respected professors, eminent scientists, research scholars, and students for the 3 days international workshop, summer school, and course preparation on solar water splitting and artificial photosynthesis, SWAP 2023 Day 3, organized by Madurai Kamaraj University, collaboration with the Institute of Energy Technology, University of Poitiers and IIT BHU, sponsored by Research Council of Norway, RUSA, Defense Research and Development Organization, CSIR, Tamil Nadu State Council of Higher Education, Tamil Nadu State Council for Science and Technology, India Science and Engineering Research Board. I want to thank all our sponsors for sponsoring this event. Now we entering into the first technical session of the day. It will be my pleasure to invite Professor S. Murugesan, School of Chemistry, Madurai Kamaraj University, on the stage as a session chair to introduce and lead the session. Our first speaker for the day, Dr. Shantanu Das, Indian Institute of Technology, IIT BHU, India, to our esteemed audience. Thank you.
Very good morning to one and all present here. So in this session, we have two lectures. One is on atomic scale nano archetypes, a new paradigm of water electrolysis and quantum devices, which will be delivered by Dr. Santanu Das from IIT BHU. And another one, lecture on design and development of materials for deactivation of emerging categories of persistent organic pollutants, which will be delivered by Subra Singh from Anna University, Chennai. In first talk, we will start with Professor Santanu Das' lecture. And before he is starting his lecture, it's my duty to introduce the speaker of this session to the audience. Dr. Santanu Das has completed his master's from Indian Institute of Technology, Banaras Indian Institute of Technology, Varanasi. Then it was known as BHU. And then he did his Ph.D. from Florida International University, USA, in Material Science and Engineering. After that, he moved as a scientist in the Department of Material Science and Engineering, University of North Texas, USA. From there, he joined the IIT Varanasi as assistant professor in the year 2016. Since then, he is continuing there. And after joining IIT Varanasi, he has been instrumental in developing various laboratory courses and teaching courses, and established a research laboratory on nanomaterials and nanotechnology and thin films for electronic energy devices. He also had many administrative experiences at BHU at various levels, and his research activity involves the synthesis, characterization, and engineering of various functional nanostructures, thin films, and including 2D graphene and 2D transition metal dichalcogenides, nanocomposites, quantum dots, nanohybrids, and nano heterostructures. For his research contribution in these fields, he has received various awards and recognitions. He is a recipient of 11th National Petrochemicals Award for the Best Innovation in the year 2022 from Ministry of Petroleum and Natural Gases, Government of India. And he has a Best Teacher Award in the year 2022 and Outstanding Ph.D. Dissertation Award in Florida University, USA. And he has secured a gold medal in IIT BHU. And he is a member of Royal Society of Chemistry, UK from 2021. He is a fellow of Indian Chemical Society and member of IEEE. He is a member of IEEE, a senior member of IEEE from 2017. His outstanding contributions in this field of research has been visible by way of more than 128 publications in reputed journals, high impact reputed journals, and he has been granted 14 patents. Some of them have been already transferred as technologies, and his H index is 33 and I-10 index of 72. And also he's been a member and fellow of other societies, but the list goes on. But with this brief introduction, I invite Dr. Santanu Das to deliver his lecture.
Okay. Thank you so much, Professor Murugesan, for introducing me to the audience. And ladies and gentlemen, students, researchers, professors, scientists, very good morning to you all. And today I'm going to talk related to atomic scale nanoarchetypes, a new paradigm of water splitting and atomic scale quantum devices. And let's start this presentation with, let me see, yeah, it's moving, perfect. So, students, a question, first question. Do you recognize this slide? Yes? No? Yeah. So, I borrowed it from someone. It's not my slide. And I must say that why should I borrow this slide? Okay? All right, students, although I don't think that I should ask question, but maybe participants, can you recognize this? No? Yeah, go ahead. What is this slide is for? Yeah, let's start. Yeah, I borrowed this slide from Professor Vante, and then and really thank you. He just borrowed this slide to me to continue my talk on his from where he ends. And the reason behind this is, you see, that word I like very much. Materials engineering comes into play. So why materials engineering comes into play? And what does this materials engineering means? That's why it start with different. It's not working. Yeah. Yeah. So materials engineers perspective, to see how this materials engineers perspective says about the materials engineering. So it is not limited to surface engineering, nanoscale engineering, interfacial engineering, obviously defect engineering, functionalization, building nano archetypes. So there is a lot more. So you see there's 3 small dots in the below. That basically signifies the actual meaning, means there is no such limitations. It's a huge, you can do anything. So I didn't include the phase engineering. I didn't include the other engineering. So there is lot of possibilities. So as a scope, I focused here today to talk specifically for 2-dimensional materials and their some sort of application related to heterostructured materials, hybrid materials, how they've been designed, how they've been used for different kind of application in nanoscale engineering. Obviously, water splitting is one of them. And I love to talk a little bit one of our work on graphene for radar absorbing materials, which is basically out of the scope of this talk, but it's a little will give you some idea how a nanoscale engineering that we are basically focusing in our lab. Followed by the atomic scale engineering for various kind of optoelectronics or 2-dimensional devices, specifically quantum devices. And then nanoscale architecturing, functionalization, electrocatalysis. Obviously, summary is one of the parts. So let's start. All right. So the world of two-dimensional materials. So that world of two-dimensional materials. What do you mean by the two-dimensional materials? Anybody? So materials having at the one atomic scale thin, having most of the properties and bondings are in two dimension and x and y, having no z axis. Okay. So that's our two-dimensional materials, but you see the list is very long. It's starting off from hexagonal boron nitride and then metals, oxide, LDH, magazines, COF, MOFs, TMDs, BP, all lot of. Now there is no limit. But what should we focus for? We are mostly focusing here graphene and two-dimensional transition metal dichalcogenates for today's talk. And this is specifically a book's definition. What do you mean by two-dimensional materials? Is a defined and you read it. But I think you guys know much better than me, since you are most advanced student on this era. Well, so what does these two-dimensional materials need the expertise to work for? You know, it is obviously physics, chemistry, chemical engineering, material science, and thermodynamics and kinetics. A lot of different knowledges are required to work on this field. End of the day, what I try to mean? It's a purely form of interdisciplinary research. So if it is an interdisciplinary research, it is really challenging. So let's start step by step. Couple of terminologies I'm going to use including two-dimensional material is called heterostructured materials, hybrid materials, and so on. So heterostructured materials. What is heterostructured materials? Heterostructured materials preliminarily defined as a semiconductor structure, basically stacking layer. You know, they have in one position with other positions. So the properties of these guys changes along is a function of its height. You see the different materials. So what are the primary things that are very important in this kind of heterostructured materials? The interface between any of these two, you know. So those interface really hetero interface. So for gallium arsenide and indium arsenide, so the interface is neither gallium nor indium. You know, they are having some sort of mix architecture. So that is the thing that heterostructure means in a generic. But what we are thinking of talking of heterostructure, yeah, it's called 2D heterostructure. So now design, and based on this design and development, it deals basically with a various type of 2D materials and their architecture. So it is vertical architecture. So if 2D materials in the center, if you put a quantum dot on top of it, is basically a nanoparticle 2D, like 0-dimensional, 2-dimensional heterostructure. While a 1-dimensional nanowire has been placed on top surface of that 2D material, is basically known as, is basically known as 2D, 1D nanostructure. So nanostructure, nanowire, nanoribbon, nano hybrid. So in a vertical architecture, these two-dimensional materials, if they stacked, they're basically known as a vertical heterostructure. If they are horizontally stitched to each other, so that's all 2D horizontal architecture. So those things are nowadays in primary focus. Obviously, if we put a 2D material on top of 3D material, obviously it's 2D, 3D hybrid architecture too. So with this all, we are also seeing that what solution process 2D materials. What is the future of these materials? Now, if you look at this slide very carefully, this lot of these 2D materials are basically solution processed, and then they try to bring up to a technological innovation. So they are basically used for drop casting, vacuum filtration, and different type of spin coating, but the scale up was in challenge. Now after this, technology comes like atomatized high throughput, and then spray coating, 3D printing, inkjet printing, and those things basically improve its scalability. Means the reliability of this heterostructure now improving, because most of them are solution processed. So most of the cases that the scalability was a challenge. Now already graphene is in market, right? You know, graphene based face mask we used during the time of COVID. It was already in Indian market. Lot of other graphene based products are already in market. So but these applications are not limited to these here: sensors, solar cells, biosensor, energy storage devices, photovoltaics, of course the new transistors are coming. So that's what the entire world is running after this. So we'll show some of our work here too. So if we understand the heterostructure materials and its future, like what is its roadmap, what people are really thinking of working on it, why? So this basically gives us an idea like, okay, we still have a lot of building blocks to arrange to make a stack, to improve it. We need a lot of more effort to improve that strategies. We have to change strategies to things. And then the second one is a hybrid material. So how do you define a hybrid material? So a hybrid material is basically more broader compared to a heterostructure. Why they're broader? Because there is no limitation, 2D, 1D, 2D, 0D. So this is hybrid, you mix it. If you mix it with anything, with anyone, you can create a new architecture. That's a hybrid, but that's not heterostructure. They do not have interface. They could have homo interface. They could even have hetero interface. So there is no such limitation. If we look at step by step to this, there is a very broad area. People have been working. If you are really interested, you can go and directly read this book. It's a really nice book on hybrid material. So end of the day, is definition is basically I need to clear these things to the students. Specifically, I know the respected faculties, they knows all this, but the students, they might confuse like what is hetero and what is hybrid. So yeah, our focus already came is two-dimensional transition metal dichalcogenide, specifically molysulfide. If you look at a molysulfide, so what is its benefit? So if you see the molysulfide, it's a layered structure. One molybdenum is been sandwiched between a two sulfur layer, and they form one layer, and each and every layer been stacked to each other with a van der Waals attraction force, and that's what they basically easily been scratched off and create a monolayer. So two-dimensional material has a lot of advantage. Specifically, I'm focusing since molysulfide. So they are basically having three different phases, and that phases are basically their crystallographic architecture. So if they are in hexagonal structure, basically it's trigonal prismatic form, which is very common. It's 2H. 2HMOH2. If it is octahedral and tetragonal configuration, is basically known as 1TMOH2. And obviously there is 1 3R. It's not very explored and it's not too much interested to us. Specifically, this two phase 2H and 1T has a lot of properties is been used. So what are the basic properties? Why MOH2 is so important? First of all, they are in-plane charge transfer. The spatial charge conductivity is very high. Along with an efficient interfacial charge transfer, they also have high specific surface area. And what I suppose to not missed is band gap tunability. Now this band gap tunability means a monolayer MOH2 exhibiting the band gap of how much? 1.81 electron volt, and a multilayer MOH2 stack having a band gap of 1.2 electron volt. That means you can see there is a lot of tunability between 1.2 to 1.8, and you can choose a band gap specific along with one material, so you don't need to have to create and different stacking or something like a heterojunction kind of stuff. So that's the benefit basically comes, and then the new formation comes with an 2H and 1T. So these 2H material, 2H MOH2 is basically a semiconducting in nature, having a clear band gap, and which is basically given to our next slide here. So in this next slide, you see this 1T phase and 2H phase. They have a clear band gap of 2H, but the moment this phase transform to 2H to 1T, basically they transform into semiconducting to metallic, and that's the things are very important and aspects that been utilized for various kind of water electrolysis, water catalysis, and kind of stuff. But the question is, how many heterostructures are possible? Anybody could have any idea how many heterostructures could be possible in the world now at this moment? Yeah, don't be scared. I am not going to give you marks, So yeah, how many heterostructure possible? Any idea? 1 million maybe? 2 million? Huh? How much? Any idea? I'm sorry to say, but this is this much, you see, these are each material, and these are each material, and they are having a permutation and combination. Now you can imagine in 100 years, 1 million people working on the same field and couldn't be able to finish up the entire study of this material. So they are really huge. And specifically, what I specifically focus here, now this is just a heterostructure. Now imagine in all their dimensionality, 0D, 2D, 1D, and all the other heterostructure. Anyway, so let's not waste our time, and then let's move little bit quickly to the end, because other people are also waiting to deliver their lecture. So my first thing that I told you, the 3 things I'm going to focus on is for graphene and nano engineering or defect engineering on graphene, as specifically for using for radar absorbing materials and steel technology. Anybody has any idea what is radar absorbing material? It's basically a radar absorbent are the used for steel technology to disguise some vehicle or structure from the radar absorber. So where they're used for? Yeah, they're very famous Russian steel submarine, B-2 bomber, So those are very famous for, although they are warfare devices, but also radar absorbing also required for different type of conventional aircraft. So you see, this stealth fighter aircraft is very surface to avoid any kind of radar absorbing things. Now India also have some progress. Recently they demonstrate some sort of drone in order to create a stealth technology for specifically for defense purpose. Anybody could identify this guy? Yes? What is this guy? This. Have you seen the movie Uri? Yes? So somebody went track this guy, showing the road path, to the military people. Huh? So this is basically a drone, a bird drone, basically used for destroy the militant activity at the border in 2018. That's called Indian surgical strike. So this is a stealth drone. Basically, no one can identify this guy in a radar. So that's what it is. But let's see what is the role of a material scientist here. So what we are doing to see these things. So to develop a radar absorbing material here. So specifically, we develop graphite to graphene oxide and then reduce graphene oxide. We mix it with the polyurethane. And then we prepare a sprayable nanocomposite. And these sprayable nanocomposites are basically used for radar absorbing material. Now graphene, which is basically used to mix up with polyurethane, what kind of engineering we did there? So that's called basically defect engineering. So what is defects? I think Professor Norway gave a very deeper insight of defects. But students, what is defects? Yeah, so defects is the person was then that seat, and just from that side to she moved to that side. So she created a defects over there and moving it here. Just now Professor Sachin moved from here to outside as creating a vacancy on this chair. So that's what a defect is. So defect means something unusual which supposed not to be there. Okay? Yeah, our audience supposed to be there is full of each and every chair. But there is a lot of vacant space. So those are defects. You can think in this manner too, right? So what are the defects? So addendums and then different kind of surface reconstruction. Specifically, they have a line defect, interfacial defect, grain boundary, stacking faults, dislocations, lot of. So each and every defects, what is their role in graphene? They basically produces a cole semicircular having a localized electron concentration. So that localized electron concentration basically reflect they absorb the light, light means electromagnetic radiation. So that's what this radar, which basically sends some sort of electromagnetic radiation being absorbed by that specific devices. So this is basically having some sort of insufficient charge, and along with graphene basically produces a different kind of a magnetodielectric surface. So what kind of graphene that we are talking about? So this is basically graphene having heat treatment, different type of heat treatment, and this heat treatment was been done in microwave. And then you have a different kind of structure and architecture of graphene. You see the small ripples, small squeezed structure that's having a lot of defects there. So that defective structure basically gives us some idea like what kind of structure there. So see, with an increasing of heat treatment time, the defect concentration increases. So that's an interesting. Although the graphene oxide transform into a reduced graphene oxide, we can clearly see the X-ray peak is shifted from 002 from 10 to 20, 26 probably, yeah, 26. So that's what a typical signature of a graphene been reduced graphene oxide to reduced graphene oxide. So what is this graphene based sprayable composite? So that after making this sprayable composite of this much size, almost 1 feet by 1 feet, what we basically do, we use a transmitting antenna to send some electromagnetic signal being reflected from our sample and in receiving antenna. And that's what we measured it, that how these samples basically works. So here is the measuring setup inside an anechoic chamber. So where we have a receiving antenna, transmitting antenna, and the interesting results are here. These all are the calculations. Basically, here you see the absorptivity. So with a different frequency, you see the absorptivity is almost 100%. So to somehow increasing graphene having some sort of magnetodielectric interface along with a defect, they basically absorb the whole electromagnetic radiation, could be used for a good sprayable composite coating. So this is one of the feature, and then second one is the hybrid framework. Now the word terminology comes as a hybrid. You see the SEM, scanning electron microscopy, a small magnetic nanoparticle being infused inside the graphene layers. You see the graphene layers. So they create a framework. That framework is more beautifully seen in this TM image. You see the each and every graphene layer is been connected with a small magnetic nanoparticles, and those magnetic nanoparticles, what they do basically, they basically create an interface, and that magnetodielectric interface is basically primarily responsible for absorbing those electromagnetic radiation. Specifically, the interesting feature for this hybrid material is absorptivity in between the K region. You see the K region, there is almost 100% absorptivity. So their absorptivity increases in this frequency and completely absorb this frequency, and then it's done. So in this region, that specific device what we basically manufactured and having some sort of things, absorptivity is high. So this is our one of the publication in 2019, and it is always been in top in material science in Nature collections as always. So what is our take home message from this hybrid engineering structure or hybrid structure? This a few stuff like dielectric relaxation process under a AC electric field are creating some localized Cole semicircles, and those are the primarily responsible for the absorption. Along with this, they have reconstructed carbon framework, the graphene. They have one carbon atom goes out. What happens? They basically have some unsaturated bonds, right? So those unsaturated bonds basically have some unsaturated electrons. So localized electron concentration increases, and followed by these, they have different induced polarization centers specifically. So that electrons under AC magnetic field just dance like anything on that specific defect thing. So they just change their polarity. And followed by that residual oxygen containing chemical bonds. So those all are primarily responsible for our radar absorbing stuff. Now if we look at our second strategy, like how to develop this atomic scale two-dimensional material for optoelectronic and quantum devices. So this is not our work for first and foremost things. So in our work is something different. So this is some idea. So what are the two-dimensional atomic scale devices? So that could be a vertically stacked 2D structure, that could be a dual gated 2D heterostructure, vertical field effect transistor. Obviously, vertical field effect transistor is a different architecture. Now, my question is to the audience, do you correlate these things, and do you realize how do they prepare these things? So this molysulfide flakes is been prepared by scotch taping or taking out a single small flakes from here. So these small flakes being very unpredictable to find out on the substrate for real life devices. Then what we basically are doing, basically we are using CVD, chemical vapor deposition stuff. So this chemical vapor deposition stuff basically help us to grow two-dimensional molysulfide. So this two-dimensional molysulfide has a different architecture, CFM image, various type of star type of image, and different other architectures. So these growth on inside a chemical vapor deposition is also can be focused here. You see this, we can have a capability of growing almost 5-inch, 4 to 5-inch substrate as well. So it's a large scale device manufacturing is possible. So from there I must focus here. So this is if we have a device architecture like on p-type silicon dioxide, if it is a molysulfide and then we connect it with a different kind of electrodes. So that electrodes basically producing a different type of sensor. For example, it's used as a light sensor. So in a current voltage characteristics, we can clearly see with an induced a different amount of light concentration, basically this current changes. So it's another kind of devices where capacitance changes as a function of different type of light induced, or increase the light power, the most important. So these basically used as a photo detector or photo sensor, we basically name it as a MOS capacitor. In a second work, basically we have a large area deposition of MOS2, and that's we clearly make a devices having multi-layered structure of MOS2, which basically can be fabricated on a flexible silicon as well, along with a different type of architecture, like there are light response changes, and that light response changes with an wavelength dependent things, and these wavelength we can correlate with a various band gap of MOS2, which is typically around 1.6 in our case. So, and this is another work that we are working, has not the public, this is not published yet. So this work is we are creating a vertical junction photodiodes. So in vertical junction photodiodes, that we are trying mostly focusing on the homogeneity of that material. So this moly and sulfur, they basically are showing this Raman mapping stuff, and inside a device they clearly shows this A2G and E1G, A1G and E2G peaks showing their homogeneity. So this device basically vertical architecture basically used for another junction photodiodes. So those junction photodiodes are having some electrodes on top and bottom, and p-type silicon are junction made with molysulfide in a 2D architecture to just make a junction devices. These vertical junction devices shows various type of current changes as a function of light dose. So the increase of the dose of light, you see the changes of the current, and also their light on and off means their current versus time response are very impressive, showing they have a very clear photodetector properties. So this is a quantum devices that we focused and we are working on. So this second strategy has been done, and then the third one is I'm focusing for how nanoscale engineering basically enhances the activity of 2D materials for hydrogen generation or electrocatalysis. Yeah, we see this kind of roadmaps a lot. It's obviously not for students. Students may not understand, but I'll ask students to follow these. You see the India is showing 92% replacement of the renewable replacement of the current energy with the renewable energy. So that's India has a very big ambitious plan, and that ambitious plan was declared by our Prime Minister in Glasgow meeting, this COP meeting. In Glasgow is Conference of the Parties in 31st to 13 November. So they have strategically changes the 5 things. So one is for achieving net zero by 2070, and then having the carbon emission almost reduced by 1 billion tons by 2030. Always also increasing the renewable energy by a component up to 50% of total energy requirement by 2030, which is very ambitious. So there is no other option than hydrogen, and I think for past 2 days you guys have been attending so many discussion of, and Professor Norby, Professor Vante, they basically discussed a lot on electrolysis and hydrogen generation. Now, hydrogen is one of the most green energy India is now focusing for. Now, what is our focus of doing? This is obviously water splitting. So that's what we are being gathered here for last 3 days, and Cool Longboat project is basically focusing there too. Well, I don't want to disclose this many times. It's too somehow boring to the students. Already Professor Vante has already discussed this yesterday. Now if you are looking at a specific type of catalyst performance, that matters. Now thermodynamics matters. Thermodynamics of materials matters. So why these matters, and what is these things? This is God's energy, I say, gives free energy. So these gives free energy having very important role in hydrogen adsorption and desorption. So how hydrogen being adsorbed or dissolved, why delta GH shows the performance of the material, and that's what we design a material. We change its structure, heterostructure, and its architecture. Specifically, we know very well, like platinum and platinum group of metals having delta GH is near to 0. So that's what their catalytic performance is always been highest than any other material. So this is platinum group of materials, and we discussing a lot. But what is the strategies? What is the new strategy? What kind of things that we have been focusing for? So we are specifically focusing on this guy. So Professor Vante shows these things, the Sabatier plot. So not too high, not too low. Yesterday, these 2 legs, and that's what the volcanic plot has been formulated. And platinum is everywhere near to 0. You see, that gives free energy, means the hydrogen absorption desorption needs the lowest energy and most favorable, and that's why they are highly electrocatalytic compared to any other materials. But MOS2, which we are focusing, is not that much far away from platinum if you look at this plot. But the problem is, what is the problem? Yesterday, somebody was saying here, I don't know exactly his name. Yeah, go ahead. Unstable. Unstable? Yeah, it is not about one T-space. What is the generic problem of MOS2? The inactive basal plane. So that's a big problem of any kind of 2D material. The basal planes are not at all inactive, that's very inactive. So edge planes are mostly taking part in any kind of charge kinetics, charge transfer, any kind of things. But their spatial conductivity is too high. And that's what they could be utilized for any kind of light absorption property, that's photocatalysis, catalysis, all. Now strategically, if we want to change this, then there is a lot of things we can do. See, this phase engineering, like what Umia is basically mentioning, like 2H to 1T phase transformation. Well, there is also hybrid structure formation, heterostructure, activating basal planes, functionalization. So there is no limit, we can do anything. So we have been trying a lot by doing the engineering on MOS2. However, I will be focusing a very 2 parts, because the time constraint limits, we cannot focus everything here. So one strategy is moly nickel alloy. So that Professor Vante was discussing, that supported something, right? Some support you are talking about, SIMP or SIPS, something. So that supported layer we use nickel moly alloy as a supported for moly. So how do we use its supported things, and why nickel moly? First of all, nickel and moly are available in the in very huge form. Nickel moly can form any kind of alloy, specifically the intermetallics. The most important thing, they are extremely good in catalysis. Why they are very good in catalysis? Because nickel is a broadly recognized as excellent water dissociation center, while moly is a superior hydrogen absorption properties. So both together, jointly work together and create a beautiful. So these can be used for as a support. So how do they look like? So they look like this kind of nanoscale structures, so having MoO2 as a form. On top of these, there is a small dots, is basically called MoNi4. So these basically gives us an idea like why don't we grow MoS2 on surface of this MoNi4. So that we grow this MoS2 on the surface of MoNi4, then somebody could ask like why this kind of complex structure is going to manufacture. This basically is, first of all, this MoNi4 is metallic in nature, so they are sometimes unstable. Having MoS2 on surface, they have their edge plane vertically grown on a surface, having few layer MoS2. And if you look at this TM, so specifically this flaky MoS2 have this sharp edge plane structure, and this edge plane structure gives us an idea like how this charge transfer occurs on MoS2 surface. So we can confirm that all vertically grown MoS2 having takes place. So that's was the catalytic activity being improved. So we see the catalytic activity like Staffel slope we got 67, which is close to a platinum, which standard platinum, which is 34 for each year hydrogen evolution reaction. Second thing, the moly nickel surface. You go back. Let's go back. Let's see if this metallic rod, they are having some sort of limited surface, right? So if we change this surface with the growth of MoS2, the surface area basically increasing. So that surface area increasing, that's what this also increasing the active catalytic sites, because their H plane is basically vertically aligned. So that's what their electrochemical surface area increasing as well. Now the second part was after this hybrid structure. So in second part we have the sulfonated group functionalized MoS2. So what we do basically, we take a sulfonated molecule basically intercalated through the MoS2 surface, and then in the interlayer there is a sulfonated group inside it. So these basically create a slightly increase of the interlayer structure. Basically this is a serendipity in our lab. The story I'm going to tell you later. Let's focus on what kind of structure this we get. We got a flower like structure having little high surface area, and that we could use for our own electrocatalytic purpose. Most of our things, like most of our energy expended for this publishing this paper is just to prove where is sulfonated. Why sulfonated materials? Why these sulfonated things works? How? So these sulfonated things basically we found first in Raman spectroscopy a very tiny sulfonated peak, and that gives us a confidence that okay, sulfonation occurs. And why this sulfonation? First of all, they are having a very good charge transfer. They basically improve the charge transfer at catalytic active sites in compared to a pristine MoS2. Now, if we look at the our surface analysis, so those surface analyses are mostly for So those surface analysis basically gives us an XPS result. So this XPS result shows us with a various formation. So we have a sulfonation molecule being attached or intercalated with the surface. We don't know whether it is really attached on the surface or not, because there is no proof. We have not obtained this, honestly speaking. But we obtained there is an intercalation. How this intercalation stuff we found? We found HRTM. So if we look at HRTM, the interlayer spacing increases from 6.1 to 9.4. That's really vast and big. So if you see that increase of the interlayer structure and the sulfonated things going inside of it, and that's what it's having a lot of improvement in catalytic sites in its surface. Now, looking at the electrochemical data, we see that mostly the hydrogen generation reaction improves a lot with the sulfonation up to a certain percentage, and our Tafel slope is 57. You remember just now we discussed is 67. Now it's even improved to 57. So we are very close. We are trying to reach to 34 like platinum. So some work is still going on in our lab, and we'll hopefully will be succeeded soon. So these are the basically the supplementary data in support of our claim of stability of that materials is almost 12 hours as good stable current. We have some impedance results showing the charge transfer resistance and kinetics. And the most important part that we have focused for developing the theoretical understanding, like if sulfonated material goes to a site, if they populated over a surface of MOS2, you see the sulfonated molecule is populated on a layer of MOS2, you see sulfonated molecule populated on a layer of MOS2. So basically they created additional density of state. You see the additional blue colored sulfonated density of state. So the change of density of state, basically we believe they improve the electron concentration on the surface. Well, they also change the work function. There is also an additional electronic state being added in an additional energy due to the work function, change in work function. So these change in work function basically change the redox potential of that specific sample, and that's why they are improving the charge transfer kinetics.
Please complete
Yeah,
5 minutes.
I'm done.
5 minutes.
And of course, our work was improved, like impressive compared to the other available data and their results. So that we have already published in a applied surface science. And as a summary, I must say that emerging nanomaterials and nano architectures, although it's difficult to bring it to a shape or size, but they have a lot of possible advantages, and specifically they have a lot of other advantages to use a different application like broadband absorption, electronic and energy devices. But the electrochemical activity is sometimes not up to the mark. So that's what mostly we try to improve the electrochemical activity of those materials. Specifically, functionalized 2D materials have shown a very promising electrochemical activities. 2D MOS2 is an ideal replacement of graphene for different kind of quantum devices. And why it is so? Yeah. Maybe we will discuss. Various MOS2 hybrid structures, they have a various kind of light induced response, current injection and light induced injection of electron in the junction. They basically shows various kind of light detection behavior. So they use for different kind of photo detectors or so. But obviously this kind of works have a lot of challenges, you know. So what are these challenges? So these challenges obviously include the controllability. Now if you can realize the controllability of this material are really challenging, since there is lot of interfaces involved. So how to control those interfaces are really challenging. New emerging materials are very good for their heterostructure forms and shows various promises in new energy generation and electronic devices. But how to form those things? How long? How many? You see how many I showed you, a million trillion. Also the phase engineering recently come to a picture for MOS2, but that phase engineering also have lot of challenges. So along with this, I must show this slide, and I must remember this word. There is a plenty of rooms at the bottom. In 1959 Nobel lecture by Richard P. Feynman. Now, do you guys realize the word plenty means? You see the plenty means? Now, this plenty is basically what I feel is infinite, literally infinite. Yeah, so these all are our outcomes. We have further details. All are there, is already given to our website, all publications, our recent publications, all the people who are interested, read it all. So we have several review paper, research papers, all those things. Yeah, since money matters, so I must thank you to all my all my funding agencies, including Cool Longboat. So those are really it's not only money, it's also motivation. So if you have some funding, you are motivated to work a lot. So obviously national international fundings, and obviously IIT BHU supporting me always, giving a lab space, students, and all my international collaborators. Yeah, so thanks to them for tolerating me too much. Yeah, obviously my students. So these are the small research group in IIT BHU in nanomaterials for electronics and energy device need lab, and we all are excited. Umia already given you some idea on kind of photocatalysis or light induced photoplasmonic hydrogen generation. Vivek, this is first PhD student, is passed out. They are all are working, and yeah, my international collaborators, thank you to them. All of them are very nice and helping me all the way. I am here. Already a few people recently visited Varanasi. You all are invited to visit. So and thank you. Thank you so much. If you have any question, I'll be happy to answer.
So now the lecture is open for discussion.
Very interesting lecture. Thank you. It is on your radar absorbent materials. So just since your application is on aircrafts, so have you done any durability studies, because they are exposed to very extreme environment? And
Yeah,
also,
that kind of question.
Are they substrate specific? The coatings are
Substrate specific or not? Yeah, very good question. So let me give you first answer to a question. What are the substrates are? Aluminium, you know, the aircrafts are made out of. So I just bought a simple aluminium substrate this much big, and I coat it with a spray coating. So what is there? Polyurethane. So what polyurethane being used for? Polyurethane basically used for our this color, you know. What is this called? What this color? The building color. Outside the building they use some color for making the building paint, the house paint. So those are really durable. For at least for polyurethane, it has already well established, it's almost 10 years longevity. And the substrate we used specifically, you are correct, is aluminium. Why you choose aluminium? Because basically most of the aircrafts has been manufactured using aluminium or its alloy. Sometimes aluminium, titanium alloy. So it's aluminium. So aluminium is, that's why we choose aluminium. So that's what it's. On PMMA. If we have a, yeah, we can do that. This is a spray coating, yes, we can do that. No, hydro. We also did some board, right? ARF board or something that basically people used to use that coating for meta surface formation. So that kind of substrate we also did. They're improved.
Yeah, thank you, Santano, for this overview. I have one small question. Do you think that molybdenum disulfide can reach the feat of platinum?
Yeah, that's
You
a
talk
very
you talk about a
difficult
lot of
question to answer.
heterostructure and engineering, blah, blah, blah.
So to be very honest, Professor Vante, I must say this is really very difficult question to answer. We are doing different kind of strategies in order to reach. You see that data shows impressive TAFL slope, which is reducing. But let me explain our failure. We tried several times, but it's not reaching to platinum. Now, I have not tried to putting a platinum nanoparticle on MOS2 itself to see its caliber or capability, but is our belief that maybe some more strategies or maybe precisionally developed interface could reach, but it is exactly reaching to platinum or not, really difficult to answer. We have to explore. We need to explore a little more vigorously.
So I have one
Yeah,
question.
please.
In your last material, the sulfonated molybdenum sulfide, uh, what about the durability in the humid conditions? So suppose it absorbs water as a sulfonate group
That's what
may become
sulfonated.
acidic.
No, no, not really, because that sulfonated is interconnected through the interlayer of that MOS2 layers. So basically, sulfonated group is basically we choose because it is very durable in humid condition, in aqueous condition. So that's what we choose sulfonated. Obviously, another reason is nobody worked yet on sulfonated. So that's what the another reason is.
So in absence of any further questions, let me thank the
Yeah, thank you
Dr.
so much.
Toss
I really,
for
really
giving a
like the
wonderful lecture.
audience. Yes, they're very,
Thank you.
very
Thank you.
nice.
Thank you very much, sir, for sharing your valuable insights on the topic atomic scale nano architects. And also thank Professor Murugesan sir on behalf of the SWAP organizing team as a serving as a session, sir. Now I would like to invite Professor Murugesan sir to honor the speaker, Dr. Santanu Das, with the momentum. Now we move on to the invited session 4. I would like to invite Professor Murugesan sir on the stage as a session sir to introduce and lead the session our speaker Dr. Supra Singh, Anna University, Chennai, to our esteemed audience. Thank you.
So now the second lecture of this session, as I already told, will be delivered by Dr. Subra Singh from Anna University, Chennai, in the topic design and development of materials for deactivation of emerging categories of persistent organic pollutants. And Dr. Subra Singh has completed her MSc from Calcutta University. Of that, she has completed her Ph.D. from IIT Madras and got the best thesis award for the PhD thesis. And after that, she was being a postdoctoral fellow in France under the fellowship of CEFIPR postdoctoral fellowship award in University of Rennes, France. And then she has been as a senior project officer in Bell Consultancy Project IIT Madras and an assistant professor in Material Science Center IIT Kharagpur in the year 2012. Then she got the DST Inspire Faculty Award and joined Crystal Growth Center from 2012. And since 2016, she's been working at the Crystal Growth Center, Anna University, as a UGC assistant professor under faculty recharge program. And to her credit, she has many awards and honors. So some of them already I listed, and some of them other important awards are Professor Lashkar Best Thesis Award from IIT Madras, and she's been member of a Slack workspace office in the advisor to Government of India, and Young Female Scientist Award in the year 2016, and INSA Visiting Scientist Fellowship Award in the year 2017-18, an American Ceramic Society Appreciation for a reviewer. And then she has been awarded with many best paper awards. To her credit, she's having more than 90 publications in reputed journals, and she has already completed 8 funded projects at tune of 4 crores, and she's currently having 4 ongoing projects, and already guided 6 PhD students, and 5 PhD students are currently pursuing their PhD. Wrote 1 book and 7 book chapters, and granted with 4 patents also. And with this introduction, I invite Dr. Subra Singh to deliver her lecture.
Thank you, Professor. Thank you for the nice introduction. Am I audible? So, first of all, let me thank the organizers for having me here. It was a sudden plan, but I think it's a useful one because we have guests from all over the world, and it is really useful to have interacted over them for over the couple of days. I come from Crystal Growth Center, which is actually UGC National Research Facility, which was established around 30 years back in Anna University. So we invite students from all over India. We have a visitors program under which students can apply and they can come and stay over with us, utilize our facilities, interact with our faculty and even faculty all over the other departments. And today's topic is mostly on design and development of materials. I'm basically a physicist, ventured into material science, and now I'm here in front of all stalwarts chemists. So let me thank you for having me here once again. And before I move to the slides, let me have a word of caution. Normally when the lecture is boring, audience tend to sleep. I got up at 3 o'clock today to visit the temple. So in case I doze off in between, please wake me up. So the couple of slides. Yeah, sorry. So before I move to the topic itself, I will just take a few slides to tell the various areas which we are working on. So one of it is CO2 capture by brown millite materials, which are oxygen deficient perovskites with ordered vacancies. And this work actually was an accidental research in the sense that we noticed a color change in the sample over a period of 6 months at room temperature, and it led to this very nice work. And then from there on, we started with CO2 capture work based on brown millerites. And what was interesting in this work was a very fast reversible CO2 capture can be seen even at room temperature, and obviously the activity increases at a temperature which is the industrial flue temperature, which is 500 degrees Celsius. And this was beautifully shown in case of nano CFO, whereas in bulk CFO or calcium ferrite, you do not see any such activity. So this, if you are further interested in the paper, you can refer to the work. The second, one of my students currently is also working on the same brown millerites, which are interestingly mixed ionic electronic compounds. And these materials can be used for cathode materials, which basically it increases the triple phase boundary. I think Dr. Kalpana has shown some of this SOFC based or electrolyte and electrode based studies yesterday. There is something related to that. So the other work which our group works on is most of these are material designing of photoactive materials used for various applications, mostly energy and environmental related applications. So these are some of the works which we have recently completed, and also various other projects which are still going on. The part which I'll be discussing today is actually, does it work? I'm sorry. Yeah. So some of the, I'll be talking mostly on these 3 topics, if time permits, on the third one. So first one is basically on the photophenton process adapted for simultaneous deactivation of AMR, which is antimicrobial resistant genes, and antibiotic removal. using passivation bypassed iron based heterostructures. So this is actually a collaborative project, a DST funded project on water, and this is in collaboration Professor Indumati from IIT Madras. So we work mostly on the material development part, and they take care of the biophysics part here. So to start with, I mean, we all know why pollution is one of the important part where we need to focus on, because this is one of the problems which is faced by humanity, more so over in India, where we face both air pollution as well as water pollution, other than the soil pollution which is already existing. Now, when we go to water pollution as such, there are various levels of treatment, water treatment when you see primary levels, secondary treatment, and then comes the final stage where you also see waste related to pharmaceutical industries, hospitals, as well as drug manufacturing processing units. And these wastes, which mostly consists of antibiotics, are difficult to get rid of, mostly in the primary as well as the secondary stages. So because most of the antibiotics which we consume, I think maybe most of you know, 90% of it is excreted. And you end up having a lot of antibiotics in the source, I mean water resources, especially in water resources which are near to hospitals, pharmaceutical industries, as well as residential areas. So in future, it will not be incorrect to say that in case your doctor will prescribe tap water instead of antibiotics as such, because you don't end up using what you have. I mean, using the entire antibiotics which is prescribed to you. It all ends up in water, and it's really difficult to get rid of such antibiotics. And why is it important to remove these antibiotics from the sources? It's basically because no, it's going back, or oh, where you have to okay. Yeah, now it's come. Okay, sorry for that. So why is it why do we want to remove antibiotics? So it's basically because, am I correct? This version is there. This is better. So AMR is one of the most important problems. Why? Because the antibiotics which end up in water, the various microbes which are present in water get exposed to these antibiotics, and they become resistant to it over the time period. And when you talk about this is what is antimicrobial resistance, and when they become resistant to these antibiotics, there's a whole lot of thing which comes into effect. Mostly it affects the entire medical system, because your resistive mechanisms are all destroyed, and whatever has been developed so far doesn't work. These antibiotics will not work on the microbes in case antimicrobial resistance kicks in. So what is, and this is actually why it is one of the top 10 problems which have been focused now. WHO has already made a task force to deal with this. And so along with antibiotic removal, you also need to focus on antimicrobial resistance. So if you look into the scenario of water resources in India, starting from Ganga in the north to Hyderabad, Ayodhya in the north, as well as Hyderabad in the south, you will see antibiotics presence as well as antimicrobial resistant genes. So this is courtesy for this slide is Professor Indumati from IITM. They do a lot of sampling, and this is how we know that it exists. It exists. It is very prevalent, and even in our immediate neighborhood in Chennai, if you go to Padnikannai marshland and Alattur Lake, which are neighboring the industrial areas of pharmaceutical industries, we'll see a lot of water samples which has even the ground source as well as river sources, the canals. All of these sources have antibiotics presence and antibiotic resistance or microbial genes. Now, there have been a recent study, and the government has also released a data which says that these are the allowed levels, which are if antibiotic is present in water, it has to be within this permissible limit. So we already know where we have what we have to work towards. So this is the level which can be obtained if the water is treated, and then you will be allowed to use it for further causes. In India also, we have a task force for the last 1 decade. I mean, government has put into efforts to take care of these things using various regulations by FSSAI, as well as publication of certain guidelines. So it's important to take care of these antibiotics, but the problem is if it's undissolved, you can easily remove them through filtration. But what happens to the dissolved drugs? You need some potential catalysts, important catalysts, which can degrade this. And since you want to take care of the AMR genes, they should also be simultaneously deactivating these genes from further spread. So these are the two things which we want to achieve. So what is our next step? The solution is obviously material development and designing. One of the important processes which can achieve this, both antimicrobial resistant genes deactivation as well as antibiotic removal, is an advanced oxidative process like a photophenton process. Now, zero valent ion or ZVI nanoparticles have been one of very important materials which can take care of this, but there are certain disadvantages to this. So photophenton processes where the metallic ZVI nanoparticles or iron salts can be used in presence of H2O2 and light, solar irradiation or natural light, and they produce a lot of, the process itself produces a lot of hydroxyl radicals, which is generally called the detergent because it has a non-selective behavior. It can basically take care of all your AMR genes as well as antibiotic removal. But the disadvantage of photophenton process, though even it's scalable, when you use ZVI, even though the initial efficiency is high, but there is a passivation layer which kicks in after a certain time. So you need to take care of that. Also, there are other problems like leaching and precipitation of hydroxide, especially when you use iron salts. So what do you do? Now, what we have proposed in our work is to synthesize passivation, not completely passivation free iron copper heterostructure, but to kick in certain amount of surface compositional heterogeneity, and this is because it will prevent any direct passivation of iron. So that both why copper? Copper also shows a phenton-like behavior. So you can actually scrub iron with copper and to some extent even nickel. We have taken copper in this case because this is one of the material which have been used since ages for water. We know that we use copper vessels for drinking water. We store it overnight, and then so even if there is some contribution of copper in the treated water, it will not be toxic. So yes, we have synthesized an iron copper heterostructure. Basically, why is it expected to work is you can have a nanostructured galvanic couple when you have a Fe copper heterostructured nanoparticle, which can actually rapidly disturb this native oxide layer, exposing the free or fresh iron surfaces. The second thing is, since you are employing iron here, you can employ photophenton process, which has very high mineralization rates, and you can also take care of the photocatalytic part, because you may have, obviously you will have an iron oxide layer even though you don't want it, and along with that some copper oxide is also expected, because these are nanoparticles, they are highly reactive. How much ever you try to store them, as soon as you synthesize them freshly, you will definitely end up with a thin layer of oxide. So this was what we had expected, and then we have started to work with this material. This is the initial synthesis slide wherein you see presence of copper oxide layer. In FC10 actually is the optimized sample, wherein 10% of copper and 90% of ZVI. So it's a was initially started, and it's a co-reduction method with a black precipitate which is obtained and stored, and these samples are further used for this is the general microstructure of the sample and morphology of the samples, which tells us that these are nanoparticles basically. And yes, the surface analysis actually tells us that you have the oxide layer, both Fe oxide, iron based oxide and copper oxide, along with metallic iron and copper. And why is it important? Because the basic motivation of this study was to use both these synergistic photophenton as well as photocatalytic reaction in our case. So the optimized sample of FC10 was then used for degradation of some common persistent antibiotics. We have chosen two of them, mostly tetracycline and ciprofloxacin, because these are the two persistent ones. It's difficult to break them down, and these are also the major antibiotics which are prescribed by physicians. And we see a lot of concentration of these ciprofloxacin, tetracycline, norfloxacin in the samples which we have collected in and around Chennai. So if you see the activity, photophenton activity of iron, FC10, is much more as compared to the ZVI nanoparticles. So it's not just the activity being higher when you do a aging study. So for example, the initial efficiency may be high, but when you do an aging study, you also see that the stability of these heterostructures, Fe copper heterostructures, are much more as compared. So this work was carried out for about 7 weeks, and it shows that it has a much better stability for tetracycline concentration of 30 ppm. This the concentration which we have taken is really high. It's not the concentration which you see in water, but then for our experimental convenience, this is the concentration we start working with when we use UV visible studies. Now, to do a more better, give a more idea of quantitative results, HPLC or high performance liquid chromatography is one of the important techniques which can tell us actually the removal efficiency of these antibiotics. So you can see that the heterostructure actually has about 99.9% removal as compared to 97% of ZVI. So it's almost 10 times efficient. It is also much more stable as compared to ZVI. Now, along with tetracycline, ciprofloxacin also shows a very high removal efficiency. But in reality, when you go for real samples, you don't have a single antibiotic there. You have a mixture of antibiotics. So you should have a material which should be able to act on any number of antibiotics for that matter. We have limited our study in this case to ciprofloxacin and tetracycline together, and both of these can be simultaneously, using the same material, can be degraded up to about 99.9% and 93.4% for that matter. You can also see that the rate constants of the copper, Fe copper heterostructure is much more, almost closer to 3 times than that of ZVI itself. And the same holds for ciprofloxacin degradation also. Now, the trapping studies, as expected, shows a very prominent contribution from hydroxyl radicals, because when IPA is used, it's one of the scavenger for hydroxyl radicals. So you see there is the degradation is only 10% in case of IPA. So we can say that hydroxyl radical is one of the important species which is taking part. Along with that, you also have a contribution from electron, where silver nitride plays as a scavenger. So electron along with hydroxyl radicals in this case are the species which are taking important steps in degradation of these antibiotics. So these are some of the intermediates which are present from the LCMS analysis of mixture antibiotics. You can find out these intermediates, and why we need these intermediates is because they help us to lay down a plausible mechanism as to what is happening. So we know something is happening, but what are the intermediate steps? Basically, CIP or ciprofloxacin has a cyclopropanol ring and a piperazine ring. So depending on the steps or various intermediates present, we can propose two mechanisms. In one case, you have a removal of amine, this cyclopropanol group, leading to a lower M by Z ratio, where in CP1 intermediate is shown, and then the removal of hydroxyl group, which leads to CP3. There can also be removal of the cyclopropanol itself with this intact, which will lead to again a lower M by Z ratio. Similarly, in case of tetracycline, you have large number of double bonds with a higher electron density, and so it directly acts on this higher electron density and leads to a lower M by Z ratio. And we are still not sure whether these are toxic. We'll see that whether it's toxic or not. So another thing which we look forward to is reusing these samples. So the recyclability test tells us you can recycle these samples. These are in powder forms, and mostly centrifugation is used to take back the powder samples and then reuse the powder samples for next cycles. So process of recycling up to 3 cycles gives us a degradation rate of 89%, and leaching studies basically tells us if you have iron or copper leaching in the treated water. So if, as you can see, iron was below the detection limit, and copper concentration in the treated water is much below the permissible limit in drinking water. Now, so we have to, using the LCMS mechanism or a plausible mechanism, we have a schematic representation which shows the presence of both oxide layers of copper and presence of copper as well as iron metallic counterparts, and it shows how a synergistic effect of both photophenton with a higher mineralization rate and photocatalysis with a higher reaction rate increases efficiency of our proposed heterostructure. It also shows how the leaching decreases over time and the improvement of this material during the aging studies. Now, the bacterial disinfection studies actually tells us that what we do is you use the samples and do the toxicity studies. It gives you an optimum level of the sample which can be toxic to bacteria as such. So you have to fix a concentration below that limit and then carry out the bacterial disinfection studies. So the photophenton process here is responsible and not the material itself. So photophenton process in presence of your catalyst is responsible for these bacterial disinfection, and with FC10 or the heterostructure, we could see the inactivation of E. coli was achieved within 10 minutes of using these heterostructured samples. Now, the toxicity studies tells us whether the treated water is toxic or not as compared to the untreated water. So herein we have two complementary studies where we show using Vibrio fishery as well as E. coli using the zone inhibition method as well as the Vibrio fishery response to photocatalyst CAP samples. So the sample or water had ciprofloxacin initially. It was degraded, and at regular intervals you could see how the toxicity, the average toxicity of the material of the treated water decreases with time. Now, yes, so what I have presented till now is the first part is on powder samples. But we all know it's difficult to use these powder samples, even though I want to reutilize it. It's difficult to get, retrieve these powder samples each and every time, because every time you try to recollect it, the yield decreases, and this also affects the efficiency. So what we have tried to is immobilize these powder samples using polymers, basically. So this is what we call free floating films, because they can float and they can also treat the water simultaneously. The idea of free floating films actually comes from the fact that you have these kind of structures which can actually float, and it is also possible to coat these materials, but then porous materials such as this require a lot of photocatalysts. Even though they float only on the surface, and it's not possible for us to completely clean the water without any external force. So why we want a floating film? It's basically it doesn't need any external force. You can degrade the pollutants in large surface water bodies also, and it is retrievable as well as reusable. So to make such free floating films, you can use various templates. We have used polymer as one of the templates. You can use it as a non-conducting polymer or a conducting polymer. The efficiencies are completely different. Now, obviously, if they're in powder form, recycling and other costs increase. It also leads to a secondary pollution when you use powder samples. But when you have films, you can just treat the water, remove the sample. There is no fear of secondary pollution as such. And is it possible for you to, excuse me, the first video? And these, please play the first video. So you can, these films are very easy to synthesize. It's just casting of these polymers with your samples. A small amount of, just right click and play, it should play. There's a hyperlink. Small amount of heat treatment can actually stabilize the films. So you can mix these materials using a proper polymer and then heat it to about 140 degrees Celsius, and you get to have a film which can float and treat. Is it opening? Right click and open. I don't know if it will work, but so it is in the folder actually. It should work. Open. Right click and open. Let me try. Right click and open. Where is open this one? Can you see some open thing? Open lock. Okay. Okay. Oh, Gmail is coming, is it? I don't think we have time. We have time for that? No. So let it be. So what I wanted to show is the first video shows a film. What you can see here in water. So what happens is within minutes of you dropping the film, it starts disintegrating. And you don't end up with a film, free floating film. There's nothing left behind. But a small amount of heat treatment will actually stabilize the material and you have a free floating film. There are other materials which you can use a series of your photocatalysts for immobilizing this. For example, you have a chalcogenide here where you can synthesize the film, free floating films, and you can reuse this again and again. And why is it important to have immobilized films? What are the advantages here? Obviously, recyclability is one of the advantages. Easy handling is one of the advantages. But the science behind this is you have hydroxyl ions or radicals on the surface along with moving. Shoots, yeah. So hydroxyl or carboxyl groups on the polymers, which forms a chemical bonding with the hydroxyl groups on the surface of your photocatalysts. And PVA, if it is used, it's a very good hydrophilic polymer. It has a good flexibility. It can enhance with absorption of water. The surface area enhancement between the photocatalyst and the polymer happens, and this leads to a very good flexible film. So it's obviously beneficial over the conventional substrates, and you can have a perfect photocatalytic activity for over 20 cycles. If you look at the stability here, this is 99 to 94% for about 20 cycles of these films. Okay, so how much time do I have? I've exhausted. Okay, so let me just go to the last slide. This I didn't want to show you, but this is one of the recent studies, recent projects which we are working on. It is on photocatalytic fuel cells, wherein instead of the platinum photocathode, we use again a photo active material, so that the Fermi level difference causes pollutant removal and also generation of charge. So you can have a simultaneous energy production as well as pollutant degradation in the same experiment. So these are some of the preliminary results which we have obtained from our work. We plan to extend it further. So thank you very much. And this is not possible without my group's contribution, definitely, and my collaborators and funding agencies. Thank you.
The presentation is now open for discussion.
Yeah, excellent talk. It's really, really very.
I would, sorry for taking time through the slides. It was not moving. I don't know if it's my fault.
No, that's okay. I was just little curious of your XPS slide. So in that XPS, I saw that copper, whatever you have, is it really copper? Like, I'm sorry, but
Can
you open the slide, please?
slide? Further down.
Yeah.
Yes,
Yeah. Before
Previously.
that. Yeah, this one. That the right hand one. You see the
Yes.
copper. I think, is it copper? It's a very.
You're mentioning to this?
Yeah.
This is metallic copper.
Metallic copper.
Yes.
So
These are the satellite peaks.
Basically, yeah, satellite peaks is very noisy. That's what I was just thinking.
Yes,
like,
because you have a very small amount of copper, and that too, it's 10% starting. And then when it covers, you don't get to know where exactly it's covering. So if you imagine a spherical, let's say an ideal case spherical iron nanoparticle, your copper may be sitting anywhere. So when you do the surface analysis, the area which you look for, analyze.
And
it can't
also
be
your
possible.
XRD, the before this slide, there is an XRD data.
Yes, so there you have to deconvolute to see this one. What I've shown here is not deconvolution. Yes.
Yeah, in this.
So if you see here, this is an asymmetrical
it's a
peak.
really very broad peak. Is it
you-
amorphous or you
No,
think?
not amorphous. That's why it's not if it's amorphous, you won't get a peak anywhere near the copper.
It's a very broad peak
Yes.
actually. So it's a nanoparticle. Even also 00200 is.
See, as
is
such,
not
anyway,
at all,
for
it's a-
nanoparticles, you don't get a very sharp peak. And here, the quantity itself is very less.
Yeah. Anyway, thank you so much. It's a
Thank
nice
you.
talk. I was just.
Greetings, ma'am.
Thank you.
Thank you for a good presentation, ma'am.
Thank you.
I have a doubt that in the first couple of slides, you have said that Ca2Fe2O5 that remained stable, and you have observed the color change after 6 months.
Not after 6 months, over a period of 6 months. So initially, when you have calcium ferrite in bulk, it is actually dark brown in color. If you synthesize a nanoparticle of CFO, it's dark green in color. And then over a period of time, it turns brown over a
Up
period of 6
to
months.
when the color change happened and you
Yeah,
have
so
observed.
as I said, it was an accidental research. So it changes color, and up to a period of 6 months, it became fully brown. So that is when we started investigating. And what happens is I have not shown obviously this work.
Up to what time it was stable, ma'am?
It was stable at room temperature. It is stable about 2 weeks, and then it starts converting. But
Was
then
it a label?
yeah, if you look into the work, it is not just a surface phenomena. So the entire material changes into calcium carbonate plus iron oxide. So the brown color comes from the iron oxide actually. And then you heat it back. What is interesting is you get back the nano CFO.
The reason for color change, do you think?
That's what. So it's green in color initially, and then when it starts converting, the calcium carbonate plus Fe2O3 it is brown in color, and that is why this green color changes over time to brown.
Okay, ma'am.
And
Thank
you
you.
heat it back, you get back that green sample again.
Okay, thank you, ma'am.
Thank you.
You mentioned about a film-based photocatalytic material,
Yes.
and just wanted. Can you please tell more about it? What's the material? What's the material? I mean,
Yeah,
and
so the
then
polymers which we have used are two types. One is PVDF and the other one is PVA in one of the cases.
okay,
So PVA and DMSO is one of the solvent which was used. So
okay,
this is like at room temperature, you form a solution and then it's just drop casted. The thickness, I mean, you can control it if you're using a doctor blading technique, and any large areas sample can be made with a small heat treatment at around 80 degrees Celsius, depending on which polymer you're using. We have used at 80 degrees Celsius. Some of them have been heated at 140 degrees Celsius, and then it is stable. It doesn't
okay.
disintegrate in water.
So it can be reused multiple times.
Yes.
Okay,
Yes.
good. Yeah, thank you.
Thank
Since there are no more questions, I thank the speaker for her nice talk.
Thank you, sir.
Thank you.
Very
Thank you,
much
madam.
for patiently listening and sorry if I have taken some extra time.
Thank you very much, ma'am, for sharing your deep knowledge with us. I would like to invite Professor Murugesan sir to honor Dr. Supra Singh with a memento. It's a time for a tea break. Let us all assemble back here at 11:45. Thank you. Welcome back to the session. Now we move on to the invited session 5. I would like to invite Dr. Kalpana Singh, University of Oslo, Norway, to introduce and lead the session as a session chair. Our speaker, Dr. S. Prem Kumar, VAT Velu, to our esteemed audience. Thank you.
Good morning, everyone. It's my pleasure to invite our next speaker, Dr. S. Prem Kumar, MSc PhD. He is Assistant Professor of Physics from School of Advanced Sciences, VIT University, Vellore. He is working as a postdoctoral fellow in Professor Pradeep Group, Department of Chemistry, IIT Madras, since 2022. Before that, he worked as an assistant professor of physics in Sri Kaleshwari College, Shivakasi, for a few months. Prior to that, he was visiting research associate in the University of Newcastle, Australia for 1 year and 8 months. He has received many fellowships. One of them involves SERB and PDF fellowship to pursue postdoctoral research in ISC Bangalore, India. And he has also carried out postdoctoral research for 2 years. He did his PhD from Madurai Kamaraj University. His area of specialization is spectroscopy, computational materials chemistry, and their applications in energy conversion. His research work involves both experimental and computational work, and he has published various research articles. He did his bachelor's and master's from VHNSN College, Virudnagar, and master's from NMSS VN College, respectively. He has published various research articles. Such as in ACS, Applied Material Interfaces, Advanced Science, research in chemical intermediates, and so on. So I welcome our next speaker to start his talk.
Okay, thank you, ma'am. Thanks for your nice introduction. So first of all, I would like to thank this opportunity. For giving the wonderful, opportunity to share my research knowledge in TFT modeling of novel two-dimensional materials for gas sensing. So I am Dr. S. Prem Kumar, Assistant Professor of Physics, VIT Vellore, and of course, now I'm going to explain about. Okay. So this is my outline of my talk. First, I will give some brief introduction about the case sensors. Then I will explain what are the theoretical descriptors which can be used for analyze the case sensors. And yes. Stand here. Okay. 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 Sorry. So then I will explain how the research research topic where I am using. I contributed in that field. Okay. So first basic introduction about gas sensors. So we always know that gas sensor is nothing but it's a device which is used to detect the gases in a particular area, right? So that's a gas sensors. And so gas sensing devices are widely used in many range of applications. Generally, in the industries and medicals, in many field of research. And generally gas sensing materials should have a higher sensitivity as well as higher selectivity, and it should have a reproducibility as well as it can be like low cost, and these are the significance. If you want to make a better gas sensors, these are the things we are looking for in an experimental way. And so generally, now I'm going to talk about the two-dimensional materials. So we all know that the the two-dimensional materials are nothing but it have a atomic or molecular thickness in one particular directions, and it have attracted a lot of research interest, particularly in gas sensing applications. So here I'm meaning like two-dimensional materials means like transmetal diagonals and MOFs and COFs. Anyway, so these are the types of two-dimensional materials that I am talking about. And why two-dimensional materials? Because the two-dimensional materials have a higher large specific surface area compared to your bulk 3D nanomaterials, right? And since it's got a higher specific surface area, so we can see that there is a large number of atoms are enabled in the surface atoms. I mean, in the surface levels. So which can be act as a absorption shunters, and which can increase the sensitivity of your material or activity of your gas sensors, in many different ways. And generally the two-dimensional sensing materials have a higher charge mobility, and with a suitable band gap, we can tune the band gap of the two-dimensional materials, which are the essential factors for our gas sensing materials. Okay, where we are going to use the DFT calculations actually. So DFT calculations it's a potential tool to understand or study the the basic mechanism which is happening in a sensor actually, especially in the gas sensors. So even it's very difficult to understand or predict the very weak interactions by the experimental studies, but the DFT calculation will give the the significant information about the weak interaction between the earth surface and sensing material. So this is one of the motivation why we are using DFT to study the to analyze the gas sensing materials. And so using DFT calculation, we can predict the change in the electron structure before and after gas absorptions. So that will give the information about how our gas sensing materials it interacts with your gaseous molecules. So more than that, DFT calculation can support the experimental measurements and provide the deep understanding about the mechanism of gas sensing. And so these are the parameters we are looking for from the DFT calculations. So from the DFT calculations, we can identify the possible absorption configurations of your two-dimensional material, I mean your sensors and your gases. Then we can understand the preferred absorption sites, and we can calculate the absorption energy with respect to different absorption orientation absorption sites. Then we can also calculate the charge transfer which is happening in between the gases as well as your sensing material. That will give much more information about your sensing properties. And of course I already told you, so the electronic variation, I mean the electronic properties, how it changes before and after gas absorption also we can calculate from the TFT calculations. That will give the very important idea about the gas sensing ability of the two-dimensional materials. So generally, what are the gas sensing mechanisms are available? So when you have sensing materials which are exposed to your reactive gases, then there might be a charge transfer. Can be between from the molecule, your gas molecule to the two-dimensional materials, or from the two-dimensional materials to the gases. So there might be some charge transfer might be happen. So with respect to the charge transfer, with respect to charge transformation, I mean it can be a strong or weak interactions. But with respect to this, your resistance of your sensing materials will be changed. So with respect to the change in the resistance of your sensing materials, we can calculate we can predict the, we can find out the sensing ability of a particular two-dimensional materials. So what I mean is, here with respect to your charge change in the charge between this is your sensing material. It can be a two-dimensional materials or it can be a bulk materials, but generally I am going to talk about the two-dimensional materials because it's a large surface area. And here this is a gas molecule is NO, I mean and this is like NO2 and this is CO. So here we are talking about how the charge transfer is happening between the sensing material to your gas molecule. So this can be understood from the TFT calculations. So with respect to the change in the charge transfer, we can say that which bond is stronger and which atom side is weaker. So here we can see the substrate to your gas molecule, the energy, the electron transfer is around 0.1 electron volt. But in a CO and NO, the charge transfer is around 0.022. So which indicates that there is a significant charge transfer between your gas sensor, I mean your two-dimensional material to gas for a NO2. So this material can be used for a high sensing application, particularly for NO. So these are the important factors we are calculating from the DFT calculations that will give the information about the ability, sensitivity and selectivity of your gas sensors, especially for two-dimensional materials. So I'll talk about this. So what are the theoretical descriptors we are going to calculate from the DFT calculation, particularly for gas and service? First one is absorption orientation. So here, this is that dimetal chalconates. It's like MoSe2. So here, the ammonia NH3 can be bind in terms of with respect to nitrogen also, and there is a possibility that the hydrogen can be interact with your sulfur. So that makes there are different absorption orientations possible, right? So with respect to this, your absorption energy will change. So this is one of the descriptor we are talking from DFT, and so there's a different absorption orientation. With a different absorption orientation, you'll get a different absorption energy. That will give you some information about that how the gas molecules will interact with your two-dimensional materials. And absorption sites. So what I mean by absorption site is like here we have a pure MoSe2, and this is your molybdenum, and this is the selenite. So if it's a purest material, then all the your gas molecule will interact with homogeneously with respect to your surface. But if you are making some dopant, or if you are making some defect on SC, I mean there are mainly 6 number of defects are possible in MoSe2. So if you made some defects which is like unavoidable during your experimental studies, then with respect to your defect sets, the sensing properties of the material is changed, right? So we can calculate how the defects I mean like there are 6 different defects are possible, so we can understand which defects will be used for different gases, right? And that are the insights we are getting from DFT calculations. Then absorption energy. So what I mean by absorption energy is like this is one of the graph I have taken from some literature, and see what we are doing is we are absorbing the gases from the metal surface at different height, like 1.5, 2, and 2.5 and 3, and we are calculating the absorption energy. Generally, the absorption energy in the negative have a high feasibility, right? So here we can say that the bond length, which is higher than 2.5 Armstrong, we generally have a lower absorption, I mean very high absorption energy, the negative. So these gases will be considered, so we can say that this MoSe2 is act as a better sensor for this type of gases, I mean which have a lower I mean negatively higher absorption energy can have a better gas sensor ability, right? So that defines your the sensitivity and the selectivity of your gas sensing materials. And bonding strength we can talk about, and we can talk about the charge transfer also. And so after the intercalation, I mean after the absorption of your gas molecules with your metal surface or some two-dimensional materials, so there might be, we are expecting some change in electronic properties. So we are expecting that, but generally if it is a weak interactions, then there might be no change in change in electronic properties. But if it is a strong interaction, let's say like chemical option, and there is a bond formation between the adsorbase and your adsorbents, then we can expect some electronic properties changes, and that will give you the information about how your the interactions are happening between your adsorbents and your adsorbates. So now this is the work I did with collaboration with Dr. Sujin Madam and Dr. Smagul here. This office in platform. Our main motivation for this paper is like we have taken like pristine Cr2C. These are the mexines we are talking about, Cr2C and Fe2C, and this is the new materials, and there is no no experimental evidence was proven. I mean since these materials are not yet experimentally synthesized, so what we thought is okay, we are just considering two materials, Cr2C and Fe2C, and first we thought of okay, is it possible to make this type of structure experimentally? So we are using the calculation formation energy, or we can say like occlusive energy, to calculate the feasibility of the structural formation, let's say Cr2C and Fe2C. And we already know that the mexines, when you etch with some some etching agent like HF or seal and some other things, that it can be easily oxidized, right? So the oxidation consolidation after the etching process is unavoidable. So what we did is we have studied like two different things. We have taken the pristine Cr2C and Fe2C, then the oxidation consolidized Cr2C and Fe2C, I mean the mexines. And we have taken this one, and we are just thought of proposing these two materials for a NH3 gas sensor. So this is our idea behind this one. So these are the structure of Cr2 oxidation functionalized Cr2C. So this is your carbon, and this is your if you say like chromium, then this is a chromium, right? And this is like this is the example of oxygen functionalized your Cr2C, and this is a front view and this is a side view. So what we did is we have generated the structure first, I mean Cr2C. Then we have calculate the absorption energy. Then we have making that the action functionalized. I will explain all the conditions once after this also. And this is the structure of Cr2C. After action functionalized Cr2C. Sorry. These are the, this is the structure of Fe2C, oxygen functionalized Fe2C, and this is your iron, and this is your carbon, and this is the oxygen functionalized Fe2C, and this is your ammonia, where it's, it's going to interact with your substrate, and these are your substrates. Okay. So I already told you this Cr2C and F2C is not yet synthesized when we have published. So what we did is we have taken the whole structure of MAxins, MAxins, and we have calculated the energy of the whole MAxins. Then this is the total energy of MAxins, and this is the energy of the pure metal, and this is A, your aluminum you can say, and this is your carbides. So we use this formula to calculate the formation energy. After that we have used this one, this formation energy formula to calculate the feasibility. We always talk about the feasibility or possibility of formation of Cr2C or Fe2C. Yes, this is not possible. There are no experiments are not yet done to synthesize this material. But we propose that from the Fourier energy or formation energy, these materials are possible to synthesize experimentally, right? And we have calculated the absorption energy using this formula. Here E absorption is equal to E compressed. This is the energy, total energy of the gas molecule plus your sorbate. You can say the any gas like NH3, total energy of NH3 plus your substrate. It can be oxygen functionalized Cr2C or oxygen functionalized Fe2C, and this is the total energy of isolated substrate. It can be Cr2C as well as Fe2C. Then the total energy of Cr2CO and Fe2CO, and this is the isolates the NH3 energy. So generally, if you use this formula, your absorption energy has to be negative. If it is negative, then we can say that your absorption is higher. There is a possibility that your NH3 can interact with your substrates. If it is positive, then we can say that that there is no feasibility to find the NH3 can be this material can be added as NH3 sensor. This is a table. Yeah. So we calculate the formation energy. Here, this is the energy, for Cr2C, the formation is 0.0 minus 0.07. Then we can say that there is a possibility of formation of the Cr2C. Even the Fe2C also, it's 0.03. So what we can identify from this one is, the possibility of Cr2C, pristine Cr2C is higher compared to your Fe2C. But when it's functionalized with the oxygen, the formation is it's much more higher than the pristine material. So what we can say is, the oxygen functionate Cr2CO2 as well as the iron CO2, it's have a higher formation, formation energy compared to your pristine materials. So which means we are talking about this is stability. These molecules have a Cr2CO2 have a higher stability compared to your Cr2C, such a way that Fe2CO2 also have a higher energy. Higher stability compared to your Fe2C. But once it makes a higher stability, the interaction with your adsorbate gases is significantly decreased. That's what what we have calculated from the adsorption energy. You can see that the Cr2C, the adsorption is much more higher. It's around 1.4 minus 1.4, and but Cr2CO2 is like just 0.29. So what we can say from this one is the activity of Cr2C for the gas sensing is much more higher compared to your oxygen functionalized Cr2C. But we did a lot of absorption orientation. We have studied a lot of things, and we proposed the beta charge analysis also. So that all supports these findings. So we concluded that from the absorption energy and the beta charge analysis and the charge transfer interactions, we concluded that the Cr2C can have a higher absorption, which can be acted as a sensor for NH3, right? And yeah, this is what we are observed from this paper. And now this is one part of us. I worked in the vaccines. Then there is another paper. Very nice journals. They published in molybdenum selenide. Since I am working in molybdenum selenide and MOS2 for different purposes, not only for gas sensing, I am working for hydrogen fluorescent reactions. And this is very interesting to find. This paper can be used as a. This MOS2 can be used as a gas sensors, right? So what they have done is they also done the DFT calculations, but they have chosen carbon monoxide, carbon dioxide, NH3, NO, and NO2, which can be they consider this all the gas molecules, and they propose that with respect to the absorption energy and the charge transfer interactions, which material the MOECU2 monolayer which can be used for gas sensing. That was their aim, and they with respect to the Earth surface energy and the charge transfer interaction and everything, they conclude that we will discuss about this in upcoming slides. So this is a MOSC2 structure. I mean, this is your MOSC2 structure, and this is a front view, and this is a side view. Here, this is I mean, if you say like bond distance between the substrate to your gas molecule, this is what I mean, right? This is what I mean. The bond distance between the substrates and your gas molecule. So this is for CO, and this is for CO2, and this is for NH3, and this is for NO, and this is for NO2, right? And this is your single layer MOSC2. So what I am very much interested is the defected MOSC2, right? But this paper is dedicated for the pristine material, but they talk about the sensitivity of this MOSC2 all over these different gases, example CO, CO2, NH3, NO, and NO2. So okay, this is the absorption distance. They are calculating with respect to your substrate to your gas molecule. Here you can see that compared to the carbon, CO and CO2, where NH3 have a lower absorption distance, right? And NH3 and NO2 have a similar absorption distance compared to your all other molecules. So what we are expecting is, since the absorption distance is higher, so we can say the absorption energy will be, higher in both NH3 and NO2. So that was replicated in here also. I mean, if you calculate the absorption energy, so here NH3 and NO2 they have a higher absorption energy compared to all other molecules. Especially when you see this structure, I mean this figure, we can understand this. The molecule selenide, the molar layer of molecule selenide is have higher sensitivity in both NH3, NO, and NO2 compared to your CO and CO2, right? So because the CO and CO2 your absorption is so less, and the bond distance also it's comparatively higher compared to your all other molecules. So what we can say is your monolayer CO2 is particularly very much have high sensing properties for nitrogen having gaseous molecules. Yeah, and here we are talking about the NH3 and NO2 have similar charges, but see, I mean similar absorption energy. But here, just see this. This is a charge transfer is happening between your molybdenum selenide to your gas molecules. Here, from molybdenum selenide to your gas molecule, there is just 0.015 electrons are transferred from your substrate to your gas molecules. For for CO2 molecule, 0.025 is transferred. And here this is a very interesting thing. For NH3 only, there is a electron transfer is happening from NH3 to your material, NH3 your selenide, right? But here you can see, even though your NO2 have a higher charge transfer from your material to your gas sensors, but particularly NH3 and NO2 have a same absorption energy. But what we are expecting that your NH3 also have a higher charge transfer. But here you can see the charge transfer is very, very less. It's minus 0.029 electron, but it's like here to here it's like 0.49 electron. But the absorption is so similar. So, but then they conclude that here the charge is transferred from the molecule to here, from gas molecule to here. But here it's like it's from your substrate to here. So that's what making the NH3 is like so they believe that the molybdenum selenide is a wonderful candidate for a NH3 sensors without applying the biasing voltage. Why I'm talking about the biasing voltage is like this is another important figure here we are talking about. So this is a bond. Yeah, this is the band structure of your molybdenum selenide with your CO, and this is your CO2. The green lines indicates the contribution of your gas molecules to the particular band structure, right? And here we can see here we can see like there is not that much significant changes in the band gap. I mean, so this look like nearly same. But when you go to the NO and NO2, you can see that the band distance is enormous change. It's like the conduction band minimum is around 1 electron volt here, right? But here it's like it's very much less than compared to these materials. Particularly here you can see that for NO2 molecules, that the valence band maximum just increased, just here. So what is telling is when you apply some biasing voltage, right? So the material can be act as a higher. It will have some high sensitivity towards NO2 compared to NH3. Because that's what we are understanding this. So because here the energy gap is higher compared to this one. So if you are applying some biasing voltage, this will have a higher sensing properties compared to this one. So this is what they have concluded from their work. So in a normal, without biasing voltage, the material might have a higher sensing towards the NH3. But if you are applying some biasing voltage, so it will have a higher sensing properties for a NO2. So this is the external findings. Theoretical findings, they are predicted from the competition studies. And this is our another paper. What we did is we actually this I just skipped a lot of things in this presentation, but we are a lot of things we are still working on. We thought of using the boron carbon nitrates for nitrogen English sensors or some nitrogen content sensors. So what we really did is we synthesized the mesoporous PCN structure. I mean, how by using the hard template method, right? What we have taken is like we have taken the SPA15 template. It's a mesoporous, right? Then we have make the sucrose for a carbon source, and we have taken like Ph.D. engaged complex for a boron carbon resources. And then we just we did the polymerization at 100 degrees Celsius, but overnight. Then we carbonized that one for around 1000 degrees Celsius at different temperatures we did, and we did the HF washing. Then we formed the mesoporous PCN, porous carbon nitrate, and this is the structure of what we are proposing. I mean, with respect to the change in temperature, different concentration of boron and nitrogen is forming. So this is the structure of having like I mean, this is a model one. I mean, for a particular temperature, this is the structure, and this is another. When we are increasing temperature, we just increase the concentration of nitrogen. We are increasing some temperature, and we are getting some high nitrogen content. And here also, here the boron nitrogen content is increased. I mean, this with respect to the different experimental setup. We did the PCN, CN analysis, and with respect to the XPS analysis also, we proposed this type of structures with respect to the experimental findings. Then we thought, okay, this will be considered as a nitrogen-based sensor. But unfortunately, when we do the experimental setups, when we do the experimental analysis, the experiment comes such a way that this material have a high sensing properties for a CO2, right? Why? Because yeah. So this is a ultimate. We did for different one, but finally we are taking this structure. Why? Because this is very much close with our experimental findings, right? And this is the final structure for BCN, boron carbon nitrates, for CO2 sensors, and this is your density map for the PCN. Here you can see the deficiency in some places, which is induced by the electron deficiency in some places is induced by your boron substitution, and you can see here there is some places we can see the some electron concentration. You can see the density is very much higher in a particular places, so that is will be due to the your nitrogen substitution. Okay, and what we did is we have calculated the CO2 absorption and nitrogen NH3 ammonia absorption also in different places. So what we believe is like when you have a nitrogen substitute here, this carbon will be act as an active center, right? Because it will increase your electropositivity here, so your N can be substituted here. But that was we believed. I mean, we are expecting some molecular docking effect. I mean, molecular docking effect for charge transfer. But unfortunately, fortunately or unfortunately, what we are getting is this can be act as a better sensor for CO2. Because compared to NH3, the CO2 have a higher absorption energy. So and the experiment also they prove that. So we just taken the CO2 system to find our experimental findings. And what we have done is we have calculated the different absorption orientation. I mean, not only the vertical but horizontal also we did a lot of things, and we analyzed with respect to different distance also. And we proposed that okay, these are the 4 different possible orientation where we can say that the absorption energy is negative. We are done like 10 or 12 absorption oriented sites, but everywhere we are getting the positive absorption energy. But this is like 4 structure. What we are getting is like positive absorption energy. So we propose this again. Okay, these are the possible orientation how the CO2 can be oriented towards your in a PCN, and we have calculated the parallel charge analysis and the charge density distribution also, and from that we confirm this compared to your ammonia. I mean, your CO this material have higher sensitivity towards your CO2 sensors. I mean, that's I think that's what cell. Yeah. Thank you so much.
Thank you, Dr. S. Prem Kumar, for giving us information about sensors and the computational studies. So now the floor is open for questions.
Hello, sir.
Thank you for the talk. Sensors are important, and we need more sensors. For instance, I know that for NO and NOx sensors, there is a great need for better sensors. When we work with adsorption, it is normal in my world to talk about physisorption and chemisorption and dissociative chemisorption. And you did not say these things so often. So can you comment on whether your calculations are considering both physisorption and chemisorption at the same time, or did you concentrate on one of them?
Yes, Professor. So what we are really doing is we are relaxing the gas molecules over the sensing. You can say like two-dimensional materials in possible distance. Let's say 1.5 Armstrong to 1.275 and 1 something like this. So if the bond length is very much lesser and there is a significant electron transfer is happening in between the gas molecule and I mean we are doing our level best and we are calculating the our ultimate the thing is like how it's absorbed. We are calculating with respect to the absorption energy, right? So if the distance is like let's say 2.2 Armstrong between your sensor to your sensing material, you can like say some gas molecules it's around 2 Armstrong, then we believe that there might be some chemisorption is possible. If it's more than 2.5 Armstrong, then there is no possibility of formation of any.
Yes,
Yeah.
but
Then
there is normally an energy barrier between physisorption and chemisorption, and in your energy diagram, I only see one, let's say, energy.
energy band is
So
right.
is that chemisorbed or physisorbed
So
most typically?
yeah, in our material we always we face the physisorption only, not chemisorption.
Chemisorption,
Physisorption.
physisorption.
Yes, right,
That's
yeah.
what you
Yeah.
dealt with.
Yes, right, yeah.
But still, there was some weak electron transfer,
Yeah,
but still in the
yes,
physisorption
right,
range.
yeah.
Okay, thank you.
But when you have some defected system, we are expecting that can be chemisorption.
Thank you, Dr. Prem Kumar, for the nice talk. So I have a question regarding whether you can also predict the selectivity. I mean, you have shown
Yes, ma'am.
sensitivity
Yes,
using your theoretical studies. Is it possible to predict the
yes, ma'am.
selectivity
Actually,
of?
there are a number of possible ways they are doing this. I mean, so if you are talking about selectivity, so one paper they published, they have taken like the gases differently. I mean, first they do the CO, and same thing they are doing CO2, and they are calculating the absorption energy. This is one
Okay,
of the
so
way.
using absorption
Some
energy, it's possible
yes,
to.
right. And
Yeah.
if we some example what they are saying is like let's see we are mixing with some all the gases together how the selectivity increases and unfortunately what I am literally feeling is like DFT calculation we have to create some higher supercell to discuss to decide that one.
Yeah.
Why?
It's
Because
more
if,
complicated.
yes, right. Because the concentration of gases are increasing and how it's interact with your two-dimensional materials it is very very difficult. So what I am what people are doing is they are doing considering the molecular dynamics. They are find out they are considering the n number of supercells and they are putting like the gas molecules, that's combination of all the gases. Then they are calculating the radial distance. But in your sensor, I mean your two-dimensional materials with respect to your gas molecule. So which one have a if your radial distance, let's say you have NH3 and NO2 and CO mixture, right? So which one have a very much distance? I mean very less distance between your substrate to your gas molecule. That they are believing that that material can be act as a sensor for that particular gases. So with respect to the radial distribution only, we can calculate that one.
And can you suggest I mean, I'm not aware of any experimental study which gives you the absorption energy. Absorption energy.
Absorption we can calculate. How much it's absorbed we can calculate. But
Okay.
absorption
Which experimental technique can?
ma'am, there is
When
a,
this is your theoretical
yes, right,
studies.
yes,
I
ma'am,
mean,
yes, ma'am. But ma'am, actually we are doing in Australia, but I'm not. I don't have much idea about this. Yeah.
thank you.
Thank you for the overview. I have a question. You compare molybdenum disulfide and diselenide.
Yes.
And both present a difference in the absorption energy, right?
Yes, sir.
My question is the following. Selenium per se is a semiconductor,
Semiconductor. Yes, sir.
all right? So when selenium accepts one electron, becomes metallic. It's a similar process that you observe by calculation. What happens with molybdenum diselenide, something like that? It's possible to measure the conductivity fluctuation during the absorb process?
Yeah, actually, Professor, that's what we can. So, in a band structure, if you want to talk about, I mean, this depends upon how many electrons are transferred, right? So, if you say like we can't, for my concerns, depends upon how much electron charge transfer is happening. So, but what we can do is we can calculate the band structure before absorption and after absorption. We can calculate that. I mean, after the gas absorption. So, with respect to that, we can say that. So, actually, they also find out this after the NH3 and NO2 and NO absorption, where band gap is significantly decreased because they have a higher charge transfer, but it's not becoming a metal, but there is some charge transfer occurred but in the gas molecule to your sensors. So your semiconductor properties are decreased, the band gap is decreased, that we can calculate. But how the electron T localizations happen in between the on the substrate, that's a different scenario.
Thank you.
One quick question.
Greetings, sir. Thank you for the presentation. For a long time, I have a doubt that during the physics option, the sensor is sensing, and then the same particle is releasing. Whether the same molecule is being released or ion is released, how the interaction takes place and sensed during this physics option, whether anything is tunneled like electron or some other particle, what energy transfer interaction takes place during the physics option sensing.
See, actually, it's we can't say common for commonly, but if you have metal oxides, then we can say like we call it charge transfer interactions, metal and metal oxides. So there is a significant charge transfer will be happen, but in your metals to your gas sensors, I mean your gas molecules. But it depends upon the material. It totally depends upon the material. But if you have some carbonitrate and this type of materials, there is some different types of electron acceptor and electron donor. This type of reaction happens, right? So I mean there will be, we generally take they call it the mechanism molecular docking mechanism. So there is a significant charge transfer between your material sensors, I mean your gas, and to your two-dimensional materials. But it's not making the ionizing that much energy we don't have. If it is a physics option, the energy is very, very less, and the bond distance is like it's around it may be more than 2.5 Armstrong. So I mean the molecule will be electrostatically interact with your material if it's in a physics option. If it is a chemistry option, then different story. If it is a physics option,
Whether a less amount of ionization takes place or no ionization takes place, sir,
so ionization energy.
for physics option.
See, ionization energy, we are talking about removal of electrons, right? So that much energy we are not giving. It's not available in a physics option. Just a electrostatic interaction.
Thank you, sir.
Thank you, Dr. S. Kumar, and thank you, audience, for the questions. Now,
Thank you, sir, for sharing your valuable knowledge about with us. I would like to invite Dr. Kalpana to honor our speaker, Dr. S. Prem Kumar, with a memento. Now we move on to the next invited section. I would like to invite Dr. Kalpana Singh as a session chair to introduce the session, lead the session. Our speaker, Dr. Anuradha Ashok, Ph.D. Institute of Advanced Studies, to our esteemed audience. Thank you.
it's my pleasure to introduce Dr. Anuradha M. Ashok. She is a professor in Functional Materials Laboratory, Ph.D. Institute of Advanced Studies, Coimbatore. In her education, she has done Masters in Material Science from Mangalore University, Karnataka, PhD in Physics from University of Oslo, Norway. Her research interests includes functional oxides for clean energy applications, and she also has very well knowledge of transmission electron microscopy, crystallography, structural analysis of structure property relationships. In her achievements, she has been granted lots of research projects such as DST, DRDO, UGC on various clean energy applications. Also, she has established electron microscopy facility at PhD and she is a life member of Materials Research Society of India, Electron Microscopy Society of India, Institute for Smart Structures and Systems. She has guided 7 PhD and 4 MPhil and 50 postgraduate students. Apart from that, she is currently guiding 5 PhD students. She has also conducted various workshops and seminars as convener. She has written 13 book chapters and she has been invited to almost 40 invited lectures. She has published 50 journal articles, and few of the selected articles include ACS Applied Energy Materials, Journal of Applied Physics, Crystal Engineering Communications, International Journal of Hydrogen Energy, Journal of Alloys and Compounds, and Micron. And she has presented 60 national and international talks. So now I give the dais to Dr. Anuradha Pal.
Thank you, Dr. Kalpana. Can you hear me? Thank you, Dr. Kalpana, for the kind introduction. And thank you for the organizers of this conference for giving me an opportunity to present here. So basically, we are a research institute situated in Coimbatore. So we started just 12 years ago, and we are a small group of researchers working on several applications. Yeah. So just one slide about our institution. So currently we are a group of 13 people. So you say professor and head. That means my group is not so big. It's just a group of 4 people. So our institution, our research institution work on several research areas like healthcare, energy, device fabrication, environment, smart textiles, and optoelectronics. Basically, in my group, we work on material development for clean energy applications. So basically, my specialization is oxides, which I learned from my supervisor, Professor Truls Norway, how to manipulate, how to identify the defects, how to manipulate them for certain applications. So with that, I started my career after my PhD. I started my career at PhD Institute of Advanced Studies, trying to identify specific materials for specific application and tuning them to get the best efficiency. Specifically, my interest was on clean energy. So we tried so far several clean energy applications. Currently, 3 of my students are working on oxide materials for thermoelectrics, and we also developed transparent oxide materials for optoelectronic applications. This was also funded by DRDO. In addition, it was also tested for EMI shielding. And one of my students is currently working on all inorganic perovskite halides. And then one of my students worked on oxide photocatalysts for hydrogen generation. Today I'm going to present his work, Dr. Vijay Raghavan. And as an extension work of my PhD to get my first project, so we developed electrolyte materials for intermediate temperature oxide materials for intermediate temperature solid oxide fuel cells. And I also mentored one of the women scientists in developing chalcogenide based. This was one non-oxide based project which I mentored, development of nanostructured chalcogenide based thin film solar cells. Now coming to today's topic, complex ferrite oxides for photocatalytic applications. So the motivation for this work is, of course, for the clean energy. As you can see in this year's budget, a large amount of money has been allotted by the Indian government
for development of green hydrogen. So what is green hydrogen? So of course, hydrogen can be developed from several ways. You, with all the lectures since day before yesterday, you would have studied. I don't want to repeat anything. Basically, we want to concentrate on development of hydrogen from photocatalysis. So we wanted to develop the electrolyte materials, photocatalyst materials, oxide-based materials. And in addition, this process can also be used for the pollutant removal, basically the dye degradation. Near Coimbatore, there is a place called Tirupur. So water is, it's famous for textile industries. Of course, people in Madurai know. So generally water is highly polluted there because of the textile effluents. So we were trying to see if our photocatalysts can do degrade some of these dyes as well. So this was the motivation for our work. So, and we try to understand the requirement for this two applications. We understood that these are two different type of reactions. One is a spontaneous reaction, requires lesser activation energy, that is the dye degradation. It just needs lower activation energy. It's called downhill reaction. Of course, all you chemists are familiar about it. So we are a little bit weak in chemists, so we had to understand from this point of time. So with this point, so basically in the dye degradation reaction, larger organic molecules are broken into smaller molecules, which requires lesser energy, lesser activation energy. For example, but for the hydrogen generation from water splitting, photocatalytic water splitting, it needs a higher activation energy, and it's called uphill reaction, where individual molecules are broken into water molecules are broken into hydrogen and oxygen. So the same phenomena is also used for carbon dioxide reduction. But of course, in our work, we concentrated on water splitting. So this may be a repetition. You would have studied already how this reaction happens. So when your photocatalyst of required band gap is exposed to sunlight in the presence of water, so electron and hole is generated. The hole splits water into oxygen and hydrogen, and this hydrogen, oxygen and proton, this proton combines with the electrons to produce molecular hydrogen. This is the water splitting reaction. It has a different band gap. And coming to the dye degradation, of course, there are creation of not individual electrons and holes are physically will not be created. They will create superoxide anions and hydroxyl radicals. They attack the organic pollutants to break them into carbon dioxide and water. So this is the mechanism of the downhill reaction, which is dye degradation. So first we wanted to try to understand what is the requirement to be a photocatalytic material. Basically, the band gap, it should be a semiconducting material having theoretical band gap of 1.23 electron volt. But to be more precise, it should be 1.7 to 3.2 for visible light active and 3.2 to 3.9 for UV light active. So basically, why is this required? Basically, the photo-induced charges, that is charge separation that has happened due to the interaction of light, should be effectively separated, and they should be utilized for breaking of the molecule before they recombine. They have a certain life, that is 10 to the power minus 8 seconds. Before that, they should be separated and utilized for photocatalytic reaction. And at the same time, the band edge potentials. So, yeah, here the one is the band gap, and the band edge potential should be beyond more here to break water molecules, which is called the photo oxidation. It should be more positive than 1.23 electron volt, and and to create a reduction reaction to produce hydrogen, it should be more negative than 0. So this is also not only the band gap potentials is also very important. So, and then they should have photo corrosion resistant and also low cost for we try to use as much as possible cheaper and abundant materials, low cost materials with the low cost preparation techniques. So we try to study what are the most important materials for these kind of reactions. Of course, titanium dioxide and cadmium sulfide are the champion materials which are reported for these kind of applications. Now coming to oxides. So along with the titanium oxide, you have other complex oxide on the right hand side of this list. So they are more UV light active. We wanted to develop a visible light active materials and also using earth abundant non-toxic materials. So we concentrated on iron oxide. Iron oxide, as you can see, its reduction potential is lower than what is expected. So what we decided was to manipulate this iron oxide, so make them into use them in the form of complex oxide, like in the form of spinels and perovskites. So perovskites have this structure where you have the B cation has octahedral coordination, which is strongly supported by the A cation, which is at the center of this, and then the spinel has a general formula of Ab2O3, where both cations are having octahedral and tetrahedral coordination. And they have several advantages which we can make use of to get photocatalysts having required band gap and band edge potential. Yeah, as a first step, we started working on alkaline earth ferrites, barium, calcium, and strontium ferrites, and we synthesized them to from Sol-Gel method, and then we studied the band characteristics, band gaps and band edge potentials. We found that barium oxide has the highest. To identify first whether they are photocatalytically active and how active they are. So we conducted a simple dye degradation experiment by using a Congo red dye, and we found that, of course, barium ferrite has the highest percentage dye degradation, and calcium ferrite and strontium ferrite have above 80%. But barium ferrite, the dye underwent just adsorption. There was no actual degradation of the dye. So we could see calcium ferrite actually goes under dye degradation. So with calcium ferrite, we try to improve its degradation capability by doping with magnesium, and we found the highest dye degradation. So we identified it as most better performing photocatalysts, and then and we try to work more on this magnesium doped calcium ferrite. When we synthesized, we calcined it at the different temperature. We obtained several phases. It was multi-phase mixture at when we calcined, heat treated the Sol-Gel synthesized calcium ferrite. So we try to do band characteristics studies. We could see that, of course, most of them are can be used they had different band edge potentials and band gaps. So we tried to see how they behave for the water splitting experiments. So we had pure calcium ferrite and also combination of several other phases here. We had a calcium magnesium doped calcium ferrite with the spinel structure, the other one with the brown mineralite structure, along with magnesium ferrite and iron oxide. A composite material was obtained when we heat treated this reaction mixture at different temperatures. So when we conducted the hydrogen generation experiment on all these composites, we could see that the one with multiple phases was more effective in water splitting compared to the phase pure or more phase pure mixture. So the reason we gave was because of the larger recombination time. So the separated electrons and holes have been effectively separated so that they participate in splitting of water. So our experiments were conducted without any co-catalysts and under natural sunlight. We could report a higher water splitting capability when compared to the reported value of phase pure material, which was conducted with the platinum and ruthenium oxide co-catalyst under xenon lamp. Later, this was the spinel type of materials. Now, under perovskite materials, we worked on lanthanum ferrite to improve the photocatalytic activity. We tried to dope lanthanum divalent alkaline earth material elements in the position of lanthanum, and then since with the experience of the efficiency of magnesium, we also try to dope magnesium in lanthanum position in the lanthanum ferrite perovskite, and we studied the dye degradation characteristics. Here also we found that magnesium doped lanthanum ferrite gave the highest dye degradation. We also studied the band characteristics. So of course here also we when we got composite phase, we felt that we should pursue our experiments more on this multi-phase composite mixtures, and because we experienced that they have a better efficiency, so we found that lanthanum magnesium doped lanthanum ferrite gave the better photocatalytic activity. As you can see here, of course, magnesium doped lanthanum ferrite gave a better water splitting capability compared to other. Here again, lanthanum ferrite we synthesized with the sol-gel method and solid-state method. So maybe the surface characteristics of the nanomaterials also mattered. So with the sol-gel method synthesized lanthanum ferrite showed higher efficiency. With those we doped with the magnesium. So when sol-gel synthesized magnesium doped lanthanum ferrite gave better because they had a certain particular characteristics over the surface characteristics. Probably that's why they showed better water splitting capability. So again, in lanthanum ferrite, we attempted that with doping, we could achieve some improvement in the photocatalytic activity. Now we try to use some inexpensive catalyst and also a graphene material and make them as composites. So we combined lanthanum ferrite with the RGO, reduced graphene oxide and nickel oxide, and we studied the water splitting capability. We found that this composite lanthanum ferrite, sol-gel synthesized lanthanum ferrite with graphene and nickel oxide showed one of the highest water splitting capability. So basically it was collaborated with Dr. Parida after reading his paper. So he also worked on this composite with silver nitrate and with the light source. So we sent our sample to his lab to test. So with the nickel oxide, our nickel oxide and the graphene co-catalyst, it showed better photocatalytic activity. So this was one of also because of the we believe this. Sorry. So, yeah. We believe because of the extra electrons that was supplied by the co-catalyst and also larger recombination time in the composite form that could give this higher photocatalytic activity in this kind of composite materials. So to summarize, so we could achieve um, doping, and also in the form of nanocomposites. Oxide materials can be effective photocatalysts. Of course, we have to work more to further improve the efficiency. So now if you see in the Indian scenario everywhere, we have to see how your research outcome can be commercialized. This work is yet lot of work need to be done to get into a commercial scale, I believe. But in our experiments, we used all low-cost materials with easy preparation techniques without expensive co-catalysts, and we try to work on under natural sunlight as much as possible. So this is the summary of what we have obtained. We have obtained comparable photocatalytic output with the oxide-based materials, but still there is a lot more work to be done for further improvement and commercialization. So this was a work done by one of the student who was also a operator in the TEM, so he worked on part-time basis. There was no funding for this work, so several people have contributed and helped for this work. So basically the water splitting experiments were performed at Yogi Vemana University Kadapa and Shiksha Anusandhan University Bhubaneswar. All dye degradation experiments were conducted at our lab, PHIAS, and other people who also contributed for the band gap studies and band characteristics. We have done it in our lab, other labs. So we are grateful to all these scientists. And this is my research group, and this is Vijay Raghavan, who worked on this work. Currently, he is a research associate at IIT Madras. So this is my research group. This was the picture taken in this year's Pongal celebration. Thank you.
Dr. Anuradha for a nice talk. Now the floor is open for the questions.
I can talk while others are thinking of their questions. Thank you for the presentation. Of course, our work as a material scientist is a lot about finding materials that empirically gives better performance. But electrochemistry also needs to find out more about what is the rate limiting steps, what are the individual mechanistic steps, and which of them are slow. Can you do anything to look into that with your methodology? Maybe you said it, but maybe you could clarify it in a couple of sentences.
So basically one step is some of the catalysts, the molecules, when we conduct the dye degradation, they just absorb on the molecules, and then their reactivity entirely stops. So, and those are not of much use, and those photocatalysts which really react and break them into individual smaller molecules or break them into water, they should be pursued. And second thing is even with the different light sources, intensities, this can vary. And also the band edge potentials at what so we can't do much of the chemical analysis with our limitations, but we solely dependent on the band gap and band edge potentials. So as long as they are favorable, or if they are composite materials, it is the collective cooperation of the individual entities. One is creation of the electron hole pairs. Second thing is to keep them separated as long as possible. So as a composite, it is more effective. That's what we have observed.
But the first thing you said was adsorption. So competing adsorption, and maybe it leads back to what several have talked about in this conference, that understanding adsorption is a very important field of science. Maybe that's the limiting step after all. Thank you.
Yeah.
Any more questions? So if there are no questions, let's thank Anuradha. Sorry.
Thank you for this presentation. I have some remarks or comments, whatever.
Yeah,
it is.
that would be welcome. Yeah, thank you.
Doing photocatalysis, okay, it's not necessarily to have the energy. Okay, the energy will give you the driving force. That's why it would be interesting to see what is the photovoltage this material may deliver. That's one thing. You have the photovoltage, then how to increase the reaction. This is a heterogeneous reaction. We assume that you have the Norway instruments. So if you have a higher surface, then probably you have a chance
Yes.
to decrease the time.
Yeah.
Control
That's-
the
of course.
density of your sample, crystal site.
Yeah.
Like that.
Morphology also.
Yeah.
Sometime. Yeah.
But site.
That's why we tried different hydrothermal method and several methods. So with hydrothermal, you can do the morphology very well. But the thing is, we found that the yield of the photocatalyst that is obtained after the hydrothermal synthesis is very small. So that was up. But you have a very good scope of tuning the morphologies in that method. Yeah. So,
And the other aspect, which is very important too, we said here, is control the absorption energy, which could be induced by the charge at the surface and the species charge. So you also favor the change pH. So that potential measurement can deliver some clues in order to improve.
yeah.
experiment, okay?
Yes. I agree. Thank you.
Thank you, audience, and thank you, Dr. Anuradha, for a nice talk. Let's thanks the speaker again.
Thank you, ma'am, for sharing your valuable knowledge about with us. I would like to invite Dr. Kalpana Singh to honor our speaker, Dr. Anuradha Ashok, with the memento. Now we move on to the next invited section. I would like to invite Dr. Kalpana Singh Association Chair to introduce our lead the section, our speaker, Dr. Anna, Silesian University of Technology, Poland, to our esteemed audience. Thank you.
It's my pleasure to introduce our next speaker, Dr. Anna Kazmazirsak Belata. She is an assistant professor at Silesian University of Technology. A brief introduction. Anna received her Ph.D. degree in physics from Gdańsk University of Technology, Poland. Her research is focused on investigation of thermal and elastic properties of single crystals applied in non-linear optics. She completed her habilitation thesis in physics and obtained habilitation from University of Silesia, Poland.